So up to now, we have seen various bridges related to resistance measurement. The bridges like Kelvin's double bridge, Wheatstone bridge, all these things. Mega ohm bridge, all these are the various bridges which are useful for resistance measurement. And we generally call these bridges as DC bridges as we are supplying DC supply for the bridges. Now we'll understand AC bridges. Okay. In AC bridges, we can find these AC bridges are mainly used to find the unknown inductance, unknown capacitance of a capacitor, unknown frequency, etc. Okay. So what is the purpose of an AC bridge? AC bridge is used to measure unknown inductance, unknown capacitance, unknown frequency, a lot of different quantities which we can find using AC bridges. Okay. So in AC bridges, the difference between AC bridge and the DC bridge is the source and the detector. Okay. So the sources for AC bridges are AC sources, alternating current sources, and also oscillators. If the frequency is in the range of kilo ohms, if the frequency of the supply is in the range of kilo ohms, we can prefer oscillators. And if you are comfortable with the power frequency, which is 50 hertz, we can go for using AC sources. Okay. And another thing is that detectors. This is the major difference between an AC bridge and a DC bridge. Okay. So the sources are AC sources and oscillators, whereas the detectors are here headphones. We prefer headphones, and also uh, vibration galvanometers, as well as tuned amplifiers, as well as tuned amplifiers. Okay. So this we can use different detectors based upon the frequency range. If the frequency is in the range of 1 kilo ohms, we can prefer headphones. If the frequency is beyond that, we can prefer vibration galvanometers, and if the frequency is beyond megahertz, we can go for tuned amplifiers. Okay. So it is not important that for which frequency we can prefer this, for which frequency which we can prefer this. You can verify these things in your textbooks also. But basically, you need to know what is the different basic difference between AC bridge and DC bridges. Okay. In DC bridges, the source is a battery or a DC supply, whereas in AC bridge, the source is an AC source, and we generally prefer oscillators for the AC source if the frequency is uh, in the range of kilohertz. And in DC bridges, the detectors are the galvanometers. The galvanometers are considered or treated or used as the detectors, null detector. Here, the detector is nothing but null detector. Null detector is the thing which says whether the bridge is in balanced condition or not. Okay. So in case of DC bridges, the null detectors are the galvanometers. Whereas in case of AC bridges, we prefer headphones, or we prefer vibration galvanometers or tuned amplifiers to act as a detector. Okay. So if you observe in our laboratory, we have used headphones in order to check whether the bridge is in balanced condition or not. If the sound from the headphones is more, then we'll try to balance the bridge by changing some parameters like resistance, capacitance, inductance, these things, until we get the minimum sound. Okay, so the minimum sound in the headphones indicates that the bridge is in balanced condition, right? So this is about the basic difference between AC and DC bridges. In addition to that, the balancing of AC bridges uh, is taken from the concept of Wheatstone bridge. Okay, so if you observe the Wheatstone bridge, it has four arms, right? So this is the Wheatstone bridge with the resistance in each and every arm. So this is the Wheatstone bridge. So the concept of balancing the AC bridges is taken from the Wheatstone bridge concept, where the Wheatstone bridge balance condition indicates that the product of opposite arm resistances must be equal. So if I consider this as P, Q, R and S, so we got the null condition in case of Wheatstone bridge. Whatever may be the position of the detector, you can place the detector position here or the detector position here. Whatever may be the terminals where you place the detector, you will lead to the same balance equation. So we got the balance equation as PS into RQ. P into S is nothing but the product of these two opposite arms, and RQ is nothing but the product of these two opposite arms. Okay, so based upon this concept, which we got from Wheatstone bridge, we will derive the balance condition for AC bridges. Okay, but as we have resistance in DC bridges, you will have the impedances. Okay, even though the arm has a pure resistance, uh, generally we'll consider all as the impedances. It may be RL series combination, it may be RL parallel combination, it may be RC series combination or RC parallel combination, whatever it may be. You'll consider these as the impedances. So in place of resistance in DC bridges, we got the impedances. Okay, so we actually consider this as mm, Z1. So this is the convention which I am following. Different authors will follow different convention in the sense, I will consider the arm where I am placing the unknown inductance or unknown capacitance as the first arm, and the remaining three arms are like this. So I am considering this as Z2, and I am considering this as Z3, and this as Z4. So this is the convention which I am following. Different authors will follow different convention. So don't stick on to the convention, but understand the concept, so that you will be familiar, or you will be comfortable with any convention. Okay. So Z1 and Z4 are the two opposite arms here, and Z2 and Z3 are the two opposite arms. So here I am considering the detector. So I am saying again and again, the detector and the source must not be connected across the same terminals. If you connect like this, you will never get the balance condition. So you need to connect the source and the detector across the two terminals opposite to that. Okay, so if I connect the detector in between these two terminals, you need to connect the source in between these two terminals. If I connect the detector in between these two terminals, you need to connect the source in between these two terminals. Okay, this is the AC supply, and this is the detector, and these are the impedances at different arms. I consider this as the first arm, second arm, third arm, and fourth arm. Right now, as the names for the different impedances given, I am giving the voltages also. I am assuming this as E1, and we can consider this as E2, and we can consider this as E4, and I am considering this and the voltage across this arm as E3. Now E, which is the source voltage, if you observe or if you apply KVL for this loop, you can understand that E is the vector sum or the phasor sum of E1 and E3, or E2 and E4. How can I write now the voltage equation, the resultant voltage? So E is the source. When we are considering AC supply, we need to deal with the phasors. So the source voltage E is the resultant of E1 and E3, or the phasor sum of E1 and E3. If you apply KVL for this loop, if you can understand this fact. Okay. Now E plus E3, phasor sum of E1 and E3, or you can also write E as the phasor sum of E2 and E4. Okay. So this is about the DC bridges. Mm, equation is the product of two opposite arm resistances must be equal to the remaining two opposite arm resistances. Here also we considered, in place of resistance we considered the impedances. Hence the balance condition is, this is the generalized balance condition, which is Z1 into Z4, because 1 and 4 are the opposite impedances. Two opposite impedances must be equal to the product of these two opposite impedances. So Z1 into Z4 must be equal to Z2 into Z3, right? Now uh, as these are resistances, you only have a scalar values. The angle is there will be no angle, or the angle is 0 for each and every element. But here, as we are considering the impedances, we'll have some magnitude as well as phase angle. Now how can I represent Z1 in polar form? It can be represented with the magnitude as well as angle. So I can represent Z1 as magnitude of Z1 at an angle of theta 1, Z2 as magnitude of Z2 at an angle of theta 2, Z3 as magnitude of Z3 at an angle of theta 3. Similarly, Z4 as magnitude of Z4 at an angle of theta 4. Now substituting all these impedances in polar form in the balance equation. So the balance equation is Z1 into Z4 is equal to Z2 into Z3. Now in place of Z1, I can take it as magnitude of Z1 at an angle of theta 1 multiplied with magnitude of Z4 at an angle of theta 4, and it is equal to magnitude of Z2 at an angle of theta 2 multiplied with magnitude of Z3 at an angle of theta 3. Now when two complex quantities, this is one complex quantity which is expressed in polar form, this is another complex quantity which is also expressed in polar form. When two complex quantities are expressed in polar form or in rectangular form, here I am considering in polar form, then we can multiply the magnitude multiply these two magnitudes, you will get magnitude of Z2, magnitude of Z3. What about the angles? Theta 2 plus theta 3. So the condition for balancing of AC bridge is magnitudes of the two impedances of opposite arms must be equal to the magnitudes of the impedances of the remaining two opposite arms. This is we can consider this as a magnitude condition. We will treat this as a magnitude condition, magnitude criteria or magnitude condition. What about the angle condition? Angle condition is theta 1 plus, okay, theta 1 plus theta 4 must be equal to theta 2 plus theta 3. So for a bridge to be balanced, both the conditions must be satisfied. You can do the same analysis with substituting the impedances in rectangular form also, like R1 plus jx1 and here R4 plus jx4, like that. Uh, but this is important. So this is angle condition. Angle condition. Now tell me uh, how to check this condition. So for understanding these two, I am giving an example. Okay, let us understand this with a simple example, a very basic and simple example. You have a bridge with the arms like this. You have a AC bridge basically with the arms like this. So this is R1 as it is the first arm, and I am considering this as R3, and if you observe I am considering here an inductor. Here I have a pure inductor, and here I am considering a pure capacitor without any resistance. So this is I am considering this as L2 because it is in second arm. I am considering this as L2. As this is in fourth arm, I am considering this as C4. Okay, and this is R3, third arm. Now tell me, uh, how can you find the balance condition for this bridge? So the product of the impedances of these two opposite arms must be equal to the product of the impedances of these two opposite arms. So we can consider this as R1, and the impedance of this capacitance is 1 by j omega C4, and it must be equal to R3 into impedance of this pure capacitance is j omega L1. Now comparing the real and imaginary terms, as these both are imaginary terms, you can compare it easily and you can find the balance condition. But before that, you need to understand a fact. What is that fact? The bridge must satisfy both the magnitude condition and angle condition. Magnitude condition can however be considered. What is the magnitude of this impedance? It is 1 by omega C4 without j. And what is the magnitude of this impedance? It is omega L1. Okay, but if you observe the angle condition, what is the angle for this R1? It is theta 1. So what is this angle? 0 degrees. And what is the angle for this R3? Theta 3 is 0 degrees. And what is the angle of L2? Theta 2 is plus 90 degrees, because the current or the voltage across the inductor leads the current exactly by 90 degrees. Hence I am considering it as 90 degrees. And what about this angle? If this angle is plus 90 degrees for a pure inductor, the angle for a pure capacitor will be minus 90 degrees. So minus 90 degrees. Now if you substitute all these angles in this angle condition, theta 1 is 0 degrees, plus theta 4 is minus 90 degrees, and it is equal to theta 2 is plus 90 degrees, and theta 3 is 0 degrees. Here you are getting minus 90 degrees, and here you are getting 90 degrees. So these two are not equal. When these two are not equal, whatever may be the capacitor value C4 and whatever may be the inductor value L2, the angle will not change, right? Because these two are the pure elements, pure inductor and pure capacitor. Whatever may be the capacitor value C4 and whatever may be the capacitor value the inductor value L2, the angle will not change, but their magnitudes may change, so that you can get the magnitude condition satisfied, but the angle condition cannot be satisfied whatever may be the value of capacitance C4 and the inductor L2. Okay, so this bridge this bridge can never be balanced. This bridge can never be balanced. Why? Whatever may be the capacitor C4 and whatever may be the inductor L2, to you can increase C4 or you can decrease C4, you can increase L2 or decrease L2, the angles will not change. Angles remains unchanged. As the angles remains unchanged, you cannot obtain the equivalence between minus 90 degrees and 90 degrees. By this we can say the bridge can never be balanced. As the bridge can never be balanced, there is no purpose of finding the balance condition. It is foolishness, because we cannot balance the bridge. Whatever may be the value of L2, C4, even though you change R1, even though you change R3, the angles will not change. When the angles will not change, the bridge can never be balanced. Okay, so this is the major difficulty that we may encounter when we want to balance the AC bridges. Okay, we need to take care of the magnitudes as well as we need to take care of the angles. If both magnitude condition and the angle condition both are satisfied, then only the bridge will be balanced. The bridge will be balanced. Okay, for example, for example, I will change the position of this resistance from here to here. For example, for the same circuit, if I change the position of the resistance from here to here, for example, let me write like this. In the first arm, I am placing a resistance. In fourth arm, I am also placing a resistance. And here I am considering inductance, and here I am considering capacitance. Okay, so R1, L3, C2, and R4. Now the angle condition can be satisfied, because what is the angle for pure inductance? It is plus 90 degrees. Inductance for pure capacitance is minus 90 degrees. When you add these two angles, it will be 0 degrees. And here also the angles for these two resistances is 0. So 0 and 0. So the angle condition is satisfied. In order to get the magnitude condition, what you need to do? R1 into R4, these two products must be equal to this one. What is the impedance of L3? L3 impedance is j omega L3. And what is the impedance of C2? It is 1 by j omega C2. So j omega gets cancelled. You will have L3 by C2 is equal to R1 into R4. If I want to measure this unknown inductance L3, how can I get this? L3 is equal to R1, R4, C2. Very simple. So you got a simple, very simple balance condition. Now by changing either R1 or R4 and C2, you can get balance condition, and those are the values which you need to substitute here in order to get the unknown inductance L3. Okay, So this is a way of analyzing AC bridges, keeping in mind the magnitude condition and the angle condition. Okay, so I hope it is clear for you. These are some basics which are related to AC bridges. Okay,